Okay, so today we continue with first step analysis and moment generating function. And I will show you some beautiful examples how to use them to solve problems where it seems that the moment generating function or generating function is not even mentioned. Okay, so let's start with a problem. I don't remember the number, but anyway, yeah. So yeah. Okay, that's the problem number 1.6 and the problems collection. I will update it, I think, every week. I will add more problems to practice. I think I am ready to add some solutions, but for the moment they are without solution, but I will try to do my best to complete the file with solutions. Okay, so the problem number 1.6. I have a line of integer numbers. So we have 0, we have 1, we have -1, we have 2, we have -2.
Where can you find this problem sheet?
Everything is on wiki page. We follow the open access policy, so everything is on wiki page.
It was sent to the Telegram chat last Friday, Dash.
Okay, if you can't find on the wiki page, just let me print screen and drop in the Telegram chat, but I'm sure the link is on wiki page. So if something is missing from wiki page, then just ping me and we will, so it's uploading in the Telegram chat, but I think everything is on wiki page. So everything should be there. Video recordings, everything that is available is there. Okay, but I have copied the text of the problem in the Telegram chat for just to avoid an unnecessary time waste. Okay, we have integer numbers 0, 1, -1, and we have Winnie the Pooh. He wanders. He starts at 1, so he starts here, and every moment of time he either jumps to the right with probability 1/2, or he jumps to the left with the same probability 1/2. So as you see that you may think of his movements as of a Markov chain with infinitely many states. So obviously there are infinitely many states in this Markov chain because Winnie can reach the point 100, or he can reach the point -1 million. That's Markov chain with infinitely many states. But we're interested in a very simple question. Let's consider t will be the random variable, the first moment of time, first moment of time, when xt will be equal to 0. So he starts, x0 is 1. So starting point is 1. And every moment of time, he either jumps to the left, he either jumps to the right. So we are interested at the random moment of time when he will reach 0. And we are interested to calculate all probabilities. So the problem is to calculate all probabilities that t is equal to k. And these problems, it seems at first glance that there are no generating functions at all. So point A in these problems is more a hint. The ultimate goal is to find all probabilities. We are not interested in the generating function per se. It's a less meaningful object than probabilities. So we will use, nevertheless, the generating function as an intermediate step to calculate all the probabilities we need. Simple probabilities of lower value of t are easy to calculate without moment generating function. That's easy. So, for example, it's impossible to get from 1 to 0 without any move. So this probability is 0. For example, probability that t is equal to 1. Who can tell me this probability? The probability that t is equal to 1.
1/2.
Yeah, 1/2. But things will be complicated if we increase the value of k. So for small values of k, it's very easy. So what is the probability that you would? Yeah.
Why the probability of t equals 0 is 0? Why is it so?
Why? Because t is the first moment when we will reach 0. If you start at 1, you need to make at least one move to reach 0. You can't be simultaneously in two places. So if you start at 1 and you measure the time that you need to go to 0, imagine that 0 is his home. So that's a home. And he starts at point 1, at the point 1. And he needs at least one move to go to 0. Yeah, that's okay.
Yeah,
Initial starting point is 1. 0 is like home point. Okay, let's calculate some initial probabilities without any generating function. What is the probability that t will be equal to 2? And what is the probability that t will be equal to 3? They are easy, but the probability that t is equal to, let's say, 123 is hard, but we will do it. Okay, what is the probability that t is equal to 2?
0.
0. Yeah, why?
Because we can't go to 0 in even amount of moves.
Yeah, because if you make one move, odd position is transformed into even, and even position is transformed into odd position. Hence, it's impossible to go from odd 1. 1 is an odd number. It's impossible to go from 1 to 0 in even number of moves. And what is probability that t equal to 3? So that's possible. What is this value? Because it's
1/2.
Yes, I think we can exactly enumerate all possibilities. To go in exactly 3 moves, you can go, I think, right, left, left. Yeah, right, left, left. Any other possibilities? Right, left, left. What else?
Left, left, right, I guess.
Which one?
Left, left, right.
No, left, left, right is not possible because it's the first moment. If you go left,
Okay, sorry.
if you start left, left, right, then your first visit will be here. First visit to x to 0.
Then it's not a half.
Yeah, the only possible sequence of moves should start from right, left, left. Because if you go left in the first minute, then you spend only 1 minute to get to point 0. Okay, so we have here 1/8. Yeah. And we can continue calculating small probabilities for small values of t. That's more or less easy by hand, but the situation will be, you see, it will be very complicated for t equal 123, because you may go right, left, right, right, left, and arrive finally at the point 0. Yeah. But for small values of k, you may do it by hand. Okay, the goal is clear. Yeah. Anyone?
Yes.
Okay, the goal is clear. Let's. First idea is very may seem at first very unnatural, but we will calculate all the probabilities at once. The first idea, we will calculate all the probabilities at once, simultaneously, all of them, not one by one, but all of them simultaneously. How it's possible to calculate infinitely many values just simultaneously? We will pack them into a Taylor expansion. So we will search the function instead of calculating p probability that t equal to 0, probability that t equal to 1, probability that t equal to 2. Instead of calculating them one by one, we will calculate one function to rule them all. We will calculate the following function. So I will denote these unknown probabilities by P0, P1, P2, and so on. So I need to calculate these values. And I will pack these values into a Taylor expansion. I will calculate the function, and hence I will calculate all the probabilities at once. So instead of searching them one by one, I will calculate first this function. So instead of calculating these values, I will calculate one function. So if I will calculate the value of this function, then I'm done, because if I know this function, for example, if g of u is equal to, let's say, 0, so we know the beginning even, 1 over 2, sorry, it's 0 plus 1 over 2 times u power 1 plus 0 times u power 2 plus 1 over 8 times u cube plus bum. So we know the beginning of this function. Yeah, the beginning of this function looks like this. But I need to find all the value of this function, all the values of Taylor coefficients in this function. Okay. So instead of calculating probabilities, I will calculate one function that contains all the probabilities. That's okay. The idea is clear, that instead of calculating particular numbers, I will calculate one function that contains them all. Yeah, the trick is clear.
Probably clear. I have a question. So yes. U cube, what is the coefficient?
I think 1 over 8, because we have discovered by considering all the 1 over 8, I think, yeah. To get from
yes,
1,
probably.
To get
Thank
from
you.
1 to 0 in 3 moves, you need to make exactly with probability 1 over 8, you go right, left, left, and hence you arrive from 1 to 0 in exactly 3 steps. Yeah.
Yes.
Okay. So I will add a meaning to this function. I will make this function more meaningful. So honestly speaking, this function g of u is expected value of u power t. because how expected value is calculated? Expected value is calculated, you multiply the value by the probability. This t has, so these are values of t, they are 0, 1, 2, 3, 4, 5, 6, 7, u power t has values 1, u power 1, u power 2, u power 3, u power 4, and the probability that t is equal to t are p0, p1, p2, p3, p4, and so on. And hence, expected value of u power t, you multiply value by probability, you multiply value by probability, you multiply value by probability, and hence, this function contains all our probability. So we need to calculate only one function. We calculate only one function, expected value of u power to the power t, and a second step will be extract all probabilities.
Sorry, but once again, what is u and what is g of u?
G of u is an artificial function that is a bag of all probabilities. All probabilities are stored in this function. So that's an artificial function. U is a argument of this function. So once again, what do we need to find in the original problem? In the original problem, we need to find many probabilities. We need to find probability that t equal to 1, probability that t equal to 2. Instead of searching them one by one, we pack them into one function. And so we will search for this function, we will look up for this function, we will find this function, and we will extract probabilities, store it in this function like in a bag. So this function plays the role of the container of all probabilities. Okay, so that's an artificial object. This function contains all probabilities. U is an argument of this function. Okay.
Okay.
So let's calculate this expected value. So let's calculate G of U. So that's, for example, so okay, so G of U is expected value of U to the power T. Okay, let's now apply first step analysis. To calculate this expected value, we will apply first step analysis. Let's do one step. Once again, we start from 1 and we count the number of moves to go to 0. With probability 1/2, we will reach 0 in one step, and hence t will be equal to 1. So first, let's do it graphically. So we start at 1. With probability 1/2, we will reach the state 0, and hence we finish the game. But with probability 1/2, we will be twice further from the target point. Yeah. So with probability 1/2, we get to x to the position 0 in one step. But with probability 1/2, we go further from our target position. Okay, hence t will be equal to 1. And here T seems to be unpredictable for the moment. Okay. So let's calculate let's think a little bit what changes if I'm at position 2. So let's analyze this tough case first. We start here. We start here. We start at 2, and our home is at the point 0. How this problem is related to the initial problem? To go from 2 to 0, you need to do the double way. Yeah, we may say that your way is double. So hence, you may say that to go from 2 to 0, the time is changed to, if you need random time t to go from 1 to 0 for the first time, I mean, yeah. So to get from 2 to 0, you need a random time that is distributed like the sum of two random variables with the same distribution as t. So basically, when you start from 2, so imagine any path from 2 to 0. So imagine any path from 2 to 0. Let's say right, right, left, 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 right, left, left. So that's a path from 2 to 0. Yeah. Here I'm at x equal to 3. Here I'm at x equal to 4. Here I'm at x equal to 3, x equal to 2, x equal to 1, x equal to 2, x equal to 1, and finally x equal to 0. So that's a possible trajectory to go from 2 to 0. And I may find basically two segments in this on this way. I may find first you go from 2 to 1 for the first time, and then you go from 1 to 0 for the first time. And hence, you need our total time to go from 2 to 0 is a sum of two random times. You need t1 steps to go from 2 to 1, and you need t2 steps to go from 1 to 0. And they're independent. If it took you very long time to get from 2 to 1, it doesn't influence your future, yeah, because Winnie wanders randomly to the left, to the right, independently of the past. Hence, T1 and T2 are independent, and they have the same distribution as T. T1, T2, and T, they have the same distribution. They are identically distributed. Identically distributed. Is it clear? Any questions? Because that's an important point. Now I will apply the equation of the first step analysis.
Can you again explain why T1 and T2 are independent?
Are independent. So you move randomly to the left, to the right. I say that it took you, let's say, 5 moves to go from the second floor. So you are in a very big building and you randomly go up, 1 floor up, one floor down, 1 floor up, 1 floor down. You start at the second floor, and I say it took you 5 minutes to reach the floor 1 for the first time. Does this statement contain the information about the time necessary to go from first floor to the floor number 0? No, because that's a past. So imagine that that's current time. You are here, current time. Yeah. This is RRLLL are your past steps, and they are independent from your future steps. Okay.
Okay, thanks.
Okay. Now you
Alright,
start
so-
at 0.
Can I have another question? So like
Yeah.
T1 is the history of our steps and T2 is the future of our steps, right?
So it depends at which moment of time you consider this T1 and T2.
Okay,
So
yeah,
if
thank
you
you.
start at 1, so with probability 1/2, you immediately get to 0, and t is equal to 1. If you increase, then what happens? Let's calculate how many steps you need to go from initial 1 to final position 0. So you have done one step. So t is equal to 1. You have done one step plus t1 plus t2.
Oh,
It's
why
better
do we
to say,
add them?
because we need t is the total time. T, what is t? T is the total time to get from initial 1, from starting position to the final position. Okay, let me draw the picture.
Yeah, yeah,
Okay,
I got it. So
let me draw. Let me draw. Imagine you go up. Then you have made one move. Then you go up, up, down, down, up, down, down. Okay, imagine that trajectory was like this. This is t. This is t. The number of steps that you have used to go from 1 to 0. And this t may be decomposed in this case into 3 blocks. The first block is 1. It took you 1 step to go to the right. Here you decreased your position by 1, and here you once again decreased your position by 1. So this random variable, let's call it T1, let's call it T2, and they have the same distribution as T if you do not condition on the first move to the right. Okay, that's better with a picture like this. So T has transformed into 1 plus T1 plus T2.
And what if T1 it's 75% to go right and 25% to go left? Then we could say that T1 and T2 are dependent, right?
No. T1 is the number of steps you have required to go from 2 to 1.
Yes, I understand, but what if in period T1 we had not equal possibilities, but our probability would be 75% to step right and 25% to
that
step
doesn't make
left?
sense. They are still independent.
How
Because
can it be?
imagine that consider the moment time here. Imagine the time moment is here. or imagine a guy that, so imagine that current time. T1 is in the past, T2 is in the future at this moment
Oh,
of time.
okay,
So
I
they are
understand
independent.
now.
They are independent because they do not overlap. So there is moment of time that separates T1 and T2. So they are independent. So the
Thank you very much.
are not really important here. I may change probabilities. Okay, now with probability, so what we have discovered? We have discovered that with probability 1/2, t is just 1. With probability 1/2, we should replace t by 1 plus t1 plus t2, where t1 and t2 have the same distribution as t. So that's the trick, the first step analysis. After the first step, either t is 1, either t should be replaced by 1 plus t1 plus t2, where t1 and t2 have the same distribution.
Sorry, I have a
Yeah.
question.
Yeah.
2 is the number of steps that we get from 1 to 0, yeah?
Yeah. Yeah.
So can we substitute T2 just with T, our initial T?
They have the same distribution, but they are not the same random variables because t measures, they have the same distribution, but t measures from initial moment time to, so there is a subtle difference between the same random variable and identically distributed random variable. It's not the same. So on this picture, you see that if the first, if x2 is 2, then obviously t is bigger than t2. Yeah. So if x2 is 2, yeah, then obviously t is bigger than t2. And hence, this is not the same random variable, but it has identical distribution.
Okay, thank you.
Okay, now let's move on to the equation. Let's calculate expected value of u power t. With probability 1/2, we have u to the power 1. So t is equal to 1. That is the first case. Plus, with probability 1/2, we shall replace t by 1 plus t1 plus t2. And these t1 and t2 have the same distribution as t. Hence, we have this function g of u, or maybe expected value of t is 1/2 times u plus 1/2 times expected value of u times expected value of u times t1 times expected value of u times t2. Because t1 and t2 are independent. I've got the first step equation. And I almost completed the solution of the problem. There are some technical tricks, but we are almost done. We say that g of u, the function we are searching for, is 1/2 times u plus 1/2 times u times g of u times g of u. So, and this function g of u contains all the probabilities we are trying to find. Any questions here? Because that's important step. And now we will solve quadratic equation and we will extract probabilities from this function. So that's probably the crucial step. That's a crucial step here. If you understand this, then that's the main point in the solution. Any questions here? I understand that that's not easy. I have selected a hard problem to show you how first step analysis and generating functions are applied. So in the home assignment, you will have a problem that is easier than this one, but this one is too beautiful to avoid it. Okay.
And well, yes, I have a question. So T1 and T2 are independent, but does it really mean that T1 and T2 are same variables and we can just
No, they are not
change
variables.
change
They
it
have
on G
the
of
same
U?
distribution. They have the same distribution.
So my question is why, if they have the same distribution, we can interchange expected value of U of T by that.
They have the same distribution because what is T1? T1 is a time that you need to go from the floor 2 to floor 1. So, and T2 is a time you need to go from floor 1 to floor 0. But basically any sequence that leads from floor 1 to floor 2, the same sequence of moves will lead from floor 1 to floor 0. If you can go from position 2 to position 1, RR, LLL, the same sequence RR, LLL will bring you from position 2 to position from position 1 to position 0. Yeah.
Could you please repeat what is U once again?
Sorry, any sequence. So imagine that to go from any sequence, there are a lot of sequences that moves you from 2 to 1. Yeah, for example, RR, LLL, or RLL, or RRL, I don't know, RL, LL. Yeah, there are a lot of sequences that changes your position from 2 to 1. Yeah. If your current position is x equal to 2, then after these sequences, your position will be 1. And the same sequences moves you from position x equal to 1 to position x equal to 0. They are the same sequences.
Yes, that's clear. But what is the variable U?
U is just an argument of the function. So U is a way to pack all probabilities into one function. Once again, it's a little bit before. We need to calculate a lot of numbers. We need to calculate P0, we need to calculate P1, we need to calculate P2, we need to calculate P3, and so on. We need to calculate infinitely many probabilities, okay? You understand me?
Yes.
Let's pack all these probabilities into one mathematical object, into function. How to pack infinitely many numbers into one function. There are many ways to do it, but one of the beautiful ways to do it is to pack into Taylor expansion. So,
okay, so that's just a way of compression, a lot of data.
Yeah.
So, okay,
yeah,
that's
exactly
clear.
the way
But
of compression, infinitely many numbers into one function. You are exactly right. Yeah.
But then we have like this problem with calculating expected values of steps, and we use function with expected value, like expected value of U to the power T equals something. Could you please elaborate a little bit more on this transition? So is it a moment generating function in some?
It's not moment generating function, but it can be transformed in moment generating function.
And
Okay.
when we write u to the power t, that means that we want to find an expected value of coming into 0 in t terms, right?
Yeah.
Okay,
So
thank you.
we are working with this function.
I think now it's clear.
Okay, now I think so the solution is almost finished. We need to calculate this function, so let's solve quadratic equation. I think we can go with quadratic equation. Let's say we multiply by 2u, and we will get 2g times u equal to 1 to u squared plus u squared times g squared. Yeah, and we can say that I think u squared g squared minus 2gu, I think plus 1 minus 1 plus u squared is equal to 1. Here I see, so I may use the formula with discriminant, but I'm lazy, I don't like it, so I will just complete the square. So there are different techniques to solve quadratic equations, but I'm a little bit bored to use discriminant, so I will just complete the square. It's just ug minus 1 squared equals to 1 minus u squared, and hence ug minus 1 is plus or minus square root of 1 minus u squared, and hence our final answer g of u is 1 plus or minus square root of 1 minus u squared divided by u. That's okay? So that's just a solution of quadratic equation. You can use discriminant if you like, but I prefer more. I don't like ready-made formulas. I prefer to work them out. Okay, any questions here?
Yes, still a little bit unclear transition from expected value of u to some random variable t1 to g of u.
We denote this expected value by g of u. That's a notation. We denote, this is a function, so we denote it by g of u.
Okay.
Because t1 has the same distribution, then that's the same function. t2 has the same distribution, that's the same function. So they're just a notation. We are searching for this function. Or this function is a collection of all probabilities we need. Okay, let's move on. G of u is equal to 1 plus or minus square root of 1 minus u squared over u. Okay, let's continue. Now, who remembers the Taylor expansion for a1 plus t power alpha? Who remembers the Taylor expansion? Anyone? Yoo-hoo, Taylor expansion for the... Okay, maybe, well, okay, I'm a little bit surprised, but okay, the Taylor expansion for 1 plus t squared. Who remembers from the school? It's 1 plus 2t plus t squared. That's the Taylor expansion. Okay, what is the Taylor expansion of 1 plus t cube? It's 1 plus 3t plus 3t squared plus t cube. That's a Taylor expansion. That's just the funny name of open the bracket You may say, I'm doing Taylor expansion. In general, 1 plus t power n gives you 1 plus binomial coefficient. Choose 1 from n times t plus binomial coefficient. Choose 2 from n times t squared plus choose 3 from n times t cube and so on. That's okay. Do you remember? Or that's something new? Anyone?
I remember.
Okay, thank you very much. So now we continue our g of u. It's 1. So let's let's choose it's plus or minus. One root is unnecessary. So only one root we really need. So should we choose plus or minus here? Who can tell me? Should we choose plus or minus? So first question, shall we choose plus or minus? So imagine that if we choose the root with plus, imagine that we will, so imagine here we have plus 1 minus u squared over 2, 1 over 2 over u, g of u, 1 minus. So which one do we need? In the first case, we will get 1 plus 1 minus c05 1 u squared plus c05 2 times u power 4 plus divided by u. In the right case, we will get 1 minus 1 plus c05 1 u squared minus c05 2 u power 4 plus divided by u. Okay, and we already know how our function begins. We already know g of u. We know the beginning from our simple calculations. We know that our function should start by, we know that it starts like this. We have 1 over 2 probability to get in one move, 0 probability to get in two moves. So we know the beginning of this function. So we know how the function should start. So we know that the function should start like this. We know initial terms. Initial terms. 0 plus 1 over 2 times u plus 0 times u squared plus 1 over 8 times u cube plus blah, blah, blah.
So
And
we
I
should,
see, yeah,
I said that we should have minus then.
yeah, we should have minus then. Okay, so g of u is equal to c05 1 times u minus c05 squared times u cube plus c05 3 times u power 5 minus c05 power 4 times u7 and so on. So here are our probabilities. So let's just recap how we may interpret binomial coefficient with 0.5, because I hope you remember well what is a binomial coefficient when n and k are integer numbers. I hope you remember well how to calculate, choose 3 over 5. I hope you know that it's 5 over 5 factorial over 3 factorial over 2 factorial. But I think you may be a little bit surprised that you can also do something like 0.5 or 3, yeah, or this guy. Honestly speaking, the idea is exactly the same. So how this coefficient is written, it's 5 times 4 times 3 divided by 3 factorial. Or you may say it just, in general case, C alpha power k is alpha times alpha minus 1 times alpha minus 2 times blah, 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 times alpha minus k plus 1 divided by k factorial. You may write the formula like this, and you may apply it here. And you will get 0.5 times 0.5 minus 1 times 0.5 minus 2 divided by 3 factorial. That's the honest number. And hence, we have calculated all the probabilities. For example, so let's draw a happy hedgehog. Let's draw a happy hedgehog because we have finished the solution. So let's find any probability. For example, what is the probability that t will be equal to 7? It's minus t sub index 0.5 superscript 4. Yeah. So that's the probability that t will be equal to 7. Okay, what is this number? We should write minus 0.5 times 0.5 minus 1 times 0.5 minus 2 times 0.5 minus 3 divided by 4 factorial. Yeah. And I may find any probability. For example, let's calculate the probability, and it will be positive number. Everything will be fine. Don't worry. Minus in probabilities, what the hell is going on? Everything is fine. If you calculate, there are 4 negative terms in the nominator, that's okay. 4 negative terms is fine. For example, let's calculate the probability that t is equal to, let's say, 11. What is the probability that you will get in 11 moves? So you need to discover the coefficient before u11, power 11. What is coefficient before u11? How
6.
much do we? It's c 0.5 power 6. Yeah, and is it with plus or with minus?
With minus.
Yeah, with minus. So it's minus c 0.56, and we can calculate it. That's not a problem. We can even express it with factorials. So, for example, let's calculate in maybe more common way. Let's calculate probability that t is equal to 123. So it's c 0.5 to work with I should have 124 over 2. It will be 62. 62 is an even number, so it's once again with minus. So it's minus C 6205. Hence, we can write it as minus 0.5 times 0.5 minus 1 times 0.5 minus 2 times blah, 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 blah times 0.5 minus 61 divided by 62 factorial. And if we multiply, I think, all these numbers by, so to represent it in a more readable way, we can, I think, multiply and divide by, so how many terms do we have? We have 62 terms. So we multiply and divide by 2 power 62. If we multiply and divide by 2 power 62, we will get 1, 2 minus 1, 4 minus 1, 6 minus 1, 122 minus 1. Yeah. And I think that's a more appropriate way to write probability. If you see that it's positive, it's between 0 and 1, and we're happy. Yeah. I think we have done a big job. We have done great job because we have solved rather complex problem. There are two techniques that were used. The first technique is the idea that we can pack infinitely many unknown numbers into one function. So that's the first idea. Idea one. That's idea of generating functions. In moment generating functions, you pack expected value of t squared, expected value of t cube, and so on in one function. Here it's not moment generating function, it's probability generating function, but the idea is the same. The first powerful idea we have used pack P0, P1, P2 into one function. So pack infinitely many mathematical objects into one more complex mathematical object. So that's the first idea, the idea of generating function. And second idea, the idea of first step analysis. So second powerful idea, first step analysis. This approach tells us to just consider one step and describe how situation changes after one step. Maybe it is similar to initial situation, but with some modifications. And indeed, if we move up, we need to, we have two random variables that are identically distributed to our initial random variable. So there are two powerful ideas that we used in the solution of this problem. We have a little bit of time left. So let's consider some, maybe, so let's probably have, I think, have 20 minutes. I think we have. So let's
Sorry,
solve
can
some...
I ask a question?
Yes. I'm here to answer your questions.
How did we go from having found g of u, our function g of u, when we found the root, to going binomial presentation? So I think like we used Taylor expansion there, but don't really understand it. So because we have not one t plus 1 in power of alpha, but we have square root of 1 minus u squared divided by u.
Just replace t by minus u squared.
Oh, and we get it. Okay. Thank you very much.
So that's an easy question. Okay, yeah, that's a good point. Yeah. And n is 1/2. Yeah, n is a power. So I work with this formula. I apply t equal to minus u squared and n is equal to 1/2. Okay.
And also, how do we understand that for probability of t equal to 7, we will take binomial coefficient with 4 in superscript?
I just look to the link between, so I need to take, okay, the coefficient I'm searching for is packed before u power 7. Because what was my idea of compression of infinitely many probabilities into one function? The idea was to say that P1 is a coefficient before U1. P2 is a coefficient before second power of U. P3 is a coefficient before third power of U. So my compression is a little bit natural, yeah? Coefficient Pk is the coefficient before the term number k in Taylor expansion. Yeah, so my compression is not at random. So hence, I need a coefficient to find the probability that t equal to 7. I need the coefficient before u to the power 7, and it is this guy.
Okay, and for finding probability of t equal to 123, we try to analytically see what's binomial coefficient for u in power of 123, right?
Yeah, you just need to, so I just remarked that how to go from 7 to 4. I add, so u goes up by 2, the power of u goes up by 2 every time, yeah? So it is 1, 3, 5, 7, 9, 11, and the superscript of binomial coefficient goes by 1. So to calculate the superscript of binomial coefficient, I need basically to divide the power of u by 2. To be precise, I need to add 1 and divide by 2. So 7. So 7 plus 1 divided by 2 gives me 4. 5 plus 1 divided by 2 gives me 3. Because why do I need to divide by 2? Because the power of u goes by 2 every step, and the superscript of binomial coefficient goes by 1, increases by 1. Hence, I need to divide by 2, but to be more precise, plus 1 divided by 2. Okay, so here to calculate probability that t is equal to 11, 11 plus 1 is 12, 12 divided by 2 is 6, and I remark that when I have odd superscript 1, 3, the coefficient is with plus, and when I take even superscript, the coefficient, binomial coefficient is with minus. Or if I'm lazy, I may say, let's calculate it without sign, and let's. But if we will get negative value, then let's multiply it by -1 because we are working with probabilities. Our coefficients are probabilities, so all probabilities are non-negative. So we can always forget the sign, calculate, and if we have the wrong sign, just multiply it by -1 because we know what we have. What was the goal? We have packed probabilities into this Taylor expansion. So if we extract, if we are not paying attention to the sign, so we can extract and we can take absolute value and be happy. So you can ignore. So you may write that pt equal to k is the absolute value of C05 k plus 1 over 2. Yeah, so you may say like this if you don't like to pay attention to the sign. Okay.
Okay, thank you.
May I ask a question too? Can you
Yes,
scroll a little bit up?
yes, I can.
Yeah, here. So here you have in the blue area even powers, and then you have.
I divide by u. I divide by u. If you divide even powers by u, you get odd.
Okay, thank
We
you.
have, if you remember, so here's the function. You take the Taylor expansion, and in nominator, you are right. In the nominator, you will get even powers. But if you divide by 1u, you will get odd powers. And that's completely with our, it's in agreement with our intuition, yeah? Do you remember our intuition here was that you can't have even powers in the Taylor expansion? That was our intuition in the beginning. Because you can't get from 1 to 0 in even number of steps, yeah? So if we will get non-zero coefficient before even powers of u, it means that we have made an error somewhere. But for the moment, everything is in agreement with our intuition that we have positive probabilities only for odd number of steps. So that's completely reasonable. Yeah.
Okay, thank you.
And what would be P of t equals to k, like final formula for any k?
Final formula for any k. P, so you may see it here. So pt equal to k is 0 if k is even. And for if k is odd, so let's write this formula. So in the nominator, you have so how have we obtained this 62? 62 is k plus 1 over 2 factorial, 2 to the power k plus 1 over 2. And here we have what is this value? This is k minus k 120, k minus 2, k minus so it's, so let's write this formula. Okay, let me introduce some so let's write. So first, if k is even, then probability that t equal to k is equal to 0. Now let's consider only odd cases. So now k is something like 2n plus 1. Yeah, let's consider this case. Hence 2n plus 1 is 123. And 62 is just n, or it's 2n minus 1 is better, yeah? So if 2n minus 1 is 123, then n is 62, yeah? Hence, if k is odd, k is equal to 2n minus 1, then probability that t equal to k is, in nominator, we have 2 to the power n times n factorial. And in the nominator, we have 2n minus 2 times 2n minus 4 times 2n minus 2n minus 6 times blah, 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 times 1. Yeah. So that's a formula. The probability that t is equal to n minus 1. So if you'd like to write the general case, here it is.
Okay, thank you.
So yeah, it's complex probability. So this is the easiest way I know how to calculate this probability. So that's not easy just to, oh, we will count all the combinations of L and rights. So this, I think, is much harder. I don't know how to do it with direct calculation of the number of paths from 1 to 0. That's ugly formula, I agree, but we have discovered it using 2 powerful techniques. Okay, so maybe it's time to solve something easy. So let's solve something easy. We have, I think, 7 minutes. Okay, let's solve something easy. Let's concentrate on the first idea that functions may be used to pack information about many individual numbers. So let's solve something like 2.4. We have random variable x that takes non-negative integer values. So x belongs to 0, 1, 2, 3, 4, and so on. And we know the beginning of the function g of u, expected value of x. Expected value of u power x. And this function starts with 0, 1 plus 0, 2 times u plus 0, 15 times u squared plus something else. So let's first solve a very simple problem to get this idea that we pack infinitely many probabilities into one function. My question is, what is the probability that x is equal to 0? What is the probability that x is equal to 1? What is the probability that x is equal to 2? What can you say about probability that x is equal to 3? Maybe some range. So this is, I think it would be easy if you understand something in our previous discussion. What is the probability that x is equal to 0, where it is? Anyone? Well,
Maybe it's 0.1.
yeah, exactly, 0.1. Because how do we calculate expected value of u power x? We multiply probability that it is 0 times u power 0 plus probability that is equal to 1 times u power 1 plus so on. So the answers are very straightforward here. If you have a function, how to extract probabilities packed in this function, you just copy them. Yeah, that's 0, 2, 0, 15. This is unknown, but from general logic, we can say that it's between 0 and how much do we have? 65? No, 55, I think. 55, yeah. From the general properties of probability. Yeah, any questions? So let's, in the remaining 3 minutes, once again, appreciate the idea that we can pack many constants into one function using Taylor expansion. So Taylor expansion is not for nothing. So it may be used to store information. Let's, for example, solve the problem. For 3 minutes. 3 minutes, 0.2.3. 3 minutes. You have a moment generating function, expected value of exponent of tx, tw is equal to 1 plus 2t plus 7t squared plus 20t cube plus and so on. So you have Taylor expansion of another function. And this Taylor expansion is a little bit different. It stores different information, and we need to find expected value of w, expected value of w squared, expected value of w cube. No, we have no further terms of Taylor expansion, so that's not possible to find other values. Okay, who remembers how expected values are stored in moment generating function?
We need to take derivatives probably.
Yeah, but maybe it's easy to calculate derivatives if you have Taylor expansion. Yeah, that's m prime at 0. There's m prime prime at 0. This is m prime 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 at 0. Yeah, we need to take derivatives. Hence m prime at 0. If you calculate the derivative of this Taylor expansion, what will you get? The first derivative.
T plus 7t, no, 2 plus 7t plus 20t squared probably.
Yeah, you have something like this. But if we plug t, so plus something else, but if we plug t equal to 0, we will get
Only 2.
only 2. Yeah. If we need to calculate the second derivative at 0. So there are many ways to store information in function. You may use Taylor expansion, you may use derivatives, but basically they are closely related. Yeah. If we take one more derivative, 2 will disappear. It will be 7 times 2 plus 20 times 3 times 2 times t plus tdn. And if we evaluate at 0, we will get
14.
Yeah, we will get 14. And if we will calculate one more derivative, we'll get 20 times 3 times 2 times 1 plus blah, blah, blah. And if we will calculate at 0, we will get 20 times 3 factorial. And hence, from this function, from this Taylor expansion, I can get quickly expected values. For example, variance is also very quick. 14 minus 2 squared, so it's 10. And in general, if MGF has Taylor expansion, let's say k0 times, so 1 plus k1 times t plus k2 times t squared plus k3 times t power 3 and so on, then to calculate expected value of w power n, you will get kn and multiply it by which value? So if you take the nth, the derivative number n,
By the factorial.
Yeah, by the factorial of n. Yeah. So the information is stored a little bit differently, but the same powerful idea applies. If you need to calculate infinitely many expected values, it's better to pack them into one moment generating function. And the same idea we have applied for probabilities. We have packed infinitely many probabilities into one function. That's a very useful idea. And the second idea is the first step analysis. I think that everything I've planned, I have shown the big problem, the real problem. So because this problem number 2.3, number 2.4, they are like a little bit artificial to get the idea. That's not a real application. And the previous problem, it was tough. I understand that it was hard. I understand that that's not easy. That's not the level of a home assignment, but to show you how it works in real life, how they are used to calculate complex probabilities, I think that's better to have an example like this, at least in our practice session. And in home assignment, you will get something easy, but two ideas you should catch. Pack many numbers into one function and use first step analysis. Okay, thank you very much. Have a nice evening. If you have any questions, you may contact me anytime. If something is missing on wiki page, then ping me. I will either add this information myself, either I will ping assistants or the person who is responsible for that particular part of the information, but I try to maintain wiki page and everything should be there. Thank you very much. Once again, have a nice evening.
У меня вопрос по предыдущей лекции. Можно я
Да.
пошарю экран и
Yeah.
покажу?
Я потом еще
Yes.
вопрос по этой лекции спрошу.
Yeah, you may ask. Или потом это когда? When, after, later, when means now or later, later?
Ну девушка хотела показать, сейчас я после могу.
У меня просто нет доступа
Sharing,
к экрану.
sharing, I have allowed multiple participants to share. So I think if you can, or you can send in the chat or share your screen, any way is okay.
Всё. Вот у нас было задание, нам нужно было перейти из
Подожди,
continue.
подожди. Я смотрю, я пока не вижу, где оно шерится. Мне надо свое, что ли, остановить.
Вы должны в Zoom зайти.
Да,
Ну да, если...
я вроде разрешил multiple person sharing. А где она? Я вижу себя пока что. Наверное, надо мне застопить шеринг здесь. Yeah. Now we see your iPad.
Значит, нам нужно найти MGF для того, чтобы мы из continue state перебираемся в finish state. Эту строку я понимаю, это все логично. Но вот почему мы пишем E, а тут мы пишем expected value от E? Мы разве это не раскладываем по формуле вот этой вот?
No. We use the same trick that sometimes it's easy. Okay, let's, may I share this, my screen? Yeah, I understand your question. Okay, I will try to do it. Okay, share screen. Okay, TDDims. Okay, let's go back to the practice 01. What can happen? So we have state continue, state finish, and I don't remember probabilities. Maybe P and 1 minus P or vice versa. Correct me if I'm wrong, but I hope it was P to finish and 1 minus P to cycle.
Yeah.
And we have a random number n, the number of steps. Okay, with probability P, n is equal to 1. And exponent of Tn is equal to exponent of T. Yeah, that's an easy case. Now, if we go to the initial state, n is transformed into 1 plus honestly speaking, we should call it N1. So what changes? N is a number of steps we need to do from state C to F. We spend one step to cycle, and we start in U from the point C. If we start in U from the point C, then the number of steps that is needed to finish the game is random once again. So random variable n is transformed into 1 plus n1, and then 1 has the same distribution as n. Honestly speaking, that's a different random variable, but with the same distribution. And hence, expected value of exponent Tn is equal to P times exponent of T plus 1 minus P times expected value of exponent 1 plus N1. We can take exponent of T outside, yeah, and use the same function. Is it better or no?
But why in the first summand we don't have expected value, and in the second summand we have?
Because in the first case, n is transformed into a constant. And in the second case, n is still conditionally a random variable. If you arrive at f, then condition on that information, you have a constant. Expected value of a constant is a constant. But if you go back to C, that condition on this information, your future is random once again. We are not sure about the value of n.
Okay, thank you, understood.
Okay, there is another way to prove it. Okay, so let me, okay, so if I think that's not the first step analysis, but maybe you can, okay, maybe that's not the first step analysis, but maybe that will explain you why we do such thing in first step analysis. Okay, so I will do it once again. What is the expected value of exponent of Tn? If I apply the formula directly, if I apply the formula you have written directly, then you will get P times exponent of T plus 1 minus P times P times exponent 2T plus 1 minus P squared times P times exponent 3T plus 1 minus P cube. You go 3 times in a cycle, then you go to the finish, and you require, you need 4 moves to do this. That's okay?
Yeah.
Now, let's take 1 minus P out of this expression. What we will get? Expected value of exponent of Tn, just P exponent of T plus 1 minus P exponent of T times what? Times P times exponent of T plus 1 minus P times exponent of 2T plus 1 minus P squared times P times exponent of 3T, and so on. Yeah? Do you agree with me?
Yes.
Okay, and just look at this sum and on this sum. That's the same sum. Yeah?
Okay, yeah, I see.
Yeah, that's the same sum. And hence I have the first step equation, exponent of Tn is equal to P times exponent of T plus 1 minus P times exponent of T times the same expected value. But in the first step analysis, I try to understand this transformation, and I write this directly without taking out 1 minus p outside of the brackets. So that's a proof of the same identity without first step analysis. Just remark that the similarity of expressions, but my approach, no, that's not my invention. The idea of first step analysis is not to write the whole sum, but to remark the similarity using probabilistic conditional arguments. So if you condition on the first move that goes into initial position, conditionally on that information, n is transformed into one step that is done plus and new the number of steps that are ahead in the future, but they have the same distribution as n. Okay?
Yeah, thank you very much.
Any more questions? Well, multiple sharing is allowed, so if you have questions and you need to draw something, be free. I understand that online is awful, but I
Ну,
would like it to.
я хотел спросить, да, насчет того вот сложного, насчет той сложной проблемы, вот, потому что у меня был именно вопрос, раз мы этот G от U уже посчитали сначала с какими-то коэффициентами, зачем мы еще потом эти биномиальные к ним перешли, а потом я понял, что мы на самом деле G от U изначально не посчитали, ну, то есть мы посчитали только там, по-моему, до 3 шагов или что-то такое,
Yes.
вот, а это типа мало, а
Yes,
теперь мы получили
completely
общую
right.
формулу для любого количества шагов.
Да.
Да, интересненькая задачка. Хорошо, спасибо.
Okay, if there are no more questions, then have a nice evening. But once again, if you have questions, do not hesitate to contact me in the group chat. If you are a little bit shy, then you can send me a message in private. Anything is okay. I'm a little bit late with a home assignment, but I will go sleep and publish it tomorrow morning because it's late here in China. So, but I have almost completed. Okay, see you next time, and I'm happy to answer your questions. Bye-bye.
Goodbye.